why do we need to estimate the properties? And the properties we mean a couple of thermodynamic properties and a couple of transport properties. Now, this is a very short list of the properties. I'll show you. There is a comprehensive list around more than 50 properties that Aspen Plus by default calculates. But why do we need all, let's say, to prepare the mass balance? Yeah. Sometimes we calculate the mass based on energy. A very typical example is the heat exchanger. So from the heat exchanger, if we have information of the heat input to a second stream, then we can exactly determine what should be the outlet temperature, and similarly how much material should we require if we are given with the two side temperatures, inlet and outlet temperatures. So at least for mass balance, for energy balance, what else? To verify if the properties that we are estimating are aligned with the experimental data. Yeah, that should be the first step. To validate the properties, we have to estimate first, and that also gives a cross check whether the defined thermodynamic method is rightly applicable for that system. So there are so many reasons to determine the thermodynamic properties and the transport properties. What you need to mind the difference between models and the methods. This is a particular language related to Aspen Plus. Aspen High use another language. But for Aspen Plus, one thing is the model and the other thing is the method. So the model is property models are the mathematical relations that relate different state properties with the system variables or to state properties through fundamental relations. So these are the maths relations that are used to determine different properties. And those different properties are correlated with the system variables. Most of the time this variable is the temperature, but not necessarily, there can be other variables as well. But primarily the temperature. So now you can think about so many properties that are function of temperature. For example, heat capacity is a function of temperature. Enthalpy is a function of temperature, and list all the thermodynamic energy values. Those are all function of temperatures. In transport, diffusivity, conductivity, they are the function of temperatures, though they depend on the material itself as well, but as a system variable, they are function of temperature. So whatever the math relations are that relate the property with the system variable, these are the models. And what the method is, just imagine we are making a calculation and we are trying to estimate lots of maybe 2 or 3 dozens of properties, and all those properties should be defined somehow before even we estimate them. Their math relations should be defined, and imagine every property estimation have multiple math relations. In case of vapor pressure, we can estimate with the simple Einstein equation, with the extended versions of the Einstein equations. Even there are multiple Dipper models. And similarly, imagine there are other properties, and all those properties has more than one math relations. And for one time, we can only make use of one model for all the properties. So we can clamp all the math equations, taking one equation for one property and clamp together, and then make use of selection of only one component, and that component is the method. So when we choose any method, even in the Aspen Plus window, so if we choose Pang-Robinson, that doesn't mean we are trying to make use of the Pang-Robinson equation of state that is in the thermodynamics. Actually, we are taking a complete package. That package is simply named as the Pang-Robinson, but that package also involves the estimation of diffusion coefficient that maybe doesn't have anything to do with the Pang-Robinson. And similarly, the conductivity that doesn't have anything to do with the Pang-Robinson equation. So those labels, as they are termed as the method, they are simply the labels, but those labels contain a list of other math equations for a wide range of thermodynamic and transport properties. So for one method, we only have to have one math equation for the heat capacity, one equation for the vapor pressure, one for the uh, let's say other transport properties. So that is the method. So method is in fact the collection of other models or the methods itself. Sometimes we combine the methods to make a new method. So that is another different approach. The table is there. Let's say we don't need to go one by one throughout this table. That is available for your information. But few things that I would say just try to memorize, जो कि बार-बार simulations में use होंगी. Just try to memorize them. And that is how do we select which thermodynamic method is appropriate for what kind of system. There is no obvious answer for this, but there are some general opinions or some general approaches, and that depends how system is ideal or non-ideal. And from our ideality means what kind of bonds are there between the molecules and how different molecules interact with each other. You can choose water and ethanol. Just imagine mixing 1 liter of ethanol and 1 liter of water. How much volume should we attain? It's not 2 liquid. It's less than 2 liquid. And the reason is the water molecule and the hydroxyl molecule from the ethanol, they bond very strongly with the hydrogen bonding. And that bonding makes the molecule room even smaller, so much so we don't get even a simple additive sum of their molecular values or their volume values. So that strong attractive forces cannot be simply addressed with the models that are primarily based on the assumption of the ideality. So you heard about equation of states. Yeah, there is a long list of equation of state, including the virial and the cubic equation of states. Yeah, two major classes of the equation of states. So by and large, these equation of states, they are much more suitable for the system that don't behave beyond any ideality. So the forces between similar molecules and the dissimilar molecules, if they are not strong enough to drag the molecule from the ideality behavior, then we can conveniently use equation of states. But for the system that behave non-ideally, and a typical example is the system that make azeotrops, and such system they cannot be defined by the equation of states. For those systems, activity coefficient based models are much more appropriate. And to name activity coefficient models, we have very common one, NRTL, non-random two liquid activity coefficient model. Another very common one is the Wilson. You can take advantage of any of the two. Wilson model is not very much suitable when the liquid-liquid equilibrium is established, but is equally good as NRTL is when there is only vapor-liquid equilibrium. So maybe you need to revise this table a couple of times and make a good sense what kind of the system is and what kind of math equations we should use. But the good solution is always see the recommendation. At least from the recommendation, somebody has tested it already and advised which method should be used for that kind of particular system. And if you are still not sure, then you can test it yourself. We'll solve one example to test which one model is more appropriate for, let's say, water ethanol system. So first solution should be go for the recommendation. If the recommendation is not available, then search out which model or method you have to use. And for the second case, it's always good to validate the model or the method before even conveying the answers, because the answers pretty much rely on the reliability of the method itself. So if the system is again from the petroleum, there are particular models developed for the petroleum systems, including BK10, that is very common name for refinery systems. For refrigeration system, you can see recommendations even from the equation of state named as Pang-Robinson and Soft-Redlich-Fong. There was Yeah, for steam, if we are only dealing with the power industry, we are only concerned about one component. That component is water. Then we can take advantage of the steam tables, and those steam tables are integrated in terms of maths, IAPWS, or there was one other IF97. You can have a look from the computer as well. So yeah, if this we can take assumption of the Raoult's law. If the system just behave ideally in the gas phase, ideally in the liquid phase, and there are so many other systems. For example, you can take two components from any chain. Let's say benzene and toluene. Yeah, two components from let's say alkene, alkyne, alkane. These hydrocarbons. Two consecutive components, they pretty much behave like an ideal system. So for those systems, you can take a fair approach of ideality in the gas phase as well in the liquid phase, and then you can take a fair approach of the ideal system and ideal Raoult's law as a method or the model, and other component properties clamped together to make a complete method. So some specialized based on perturbation theory, they are polymers, then this kind of methods are suitable. There is a chart given below in figure 1.2. I would say take 2 minutes to have a look into this chart. It gives a very fair direction how to choose the property methods. So if you have a good sense of your system, then almost you can come across which method should be used. And that approach is looking at the component, whether those are the polar components, even in the polar they are electrolyte or not, and then what is the operating pressure. It's a general number. If the system is more than 10 bar, then most of the time some of the applicable methods that are applicable for less than 10 bar pressure, they are not applicable for more than 10 bar pressure. That's a very generic number. There is no science behind it. It's generally an experienced number. So yeah, so even if you look, some distinction is made only based on whether the system has liquid equilibrium as well or not. So especially if you notice at the top of the distillation column, we have the condenser, and sometimes that condenser also makes dirty water, especially in case of refineries, or multiple liquid phases coexist, one organic phase and one liquid phase at the same time. We have some non-condensable phase as well in the gas phase. So if those three phases are applicable even in the condenser, then some of the models are applicable and some are not applicable for that system. Having a good sense of the actual system, that guides toward what kind of method we should have. Again, look for the recommendation and look for let's say what of the method is applicable. You can test it yourself as well. The easier one is, if you don't have that detailed information, you can test Aspen built-in feature as well. So for built-in feature, that is method assistant tool. You can open Aspen Plus interface. Let's say we are not choosing any template so far. Just go to a new simulation. In the second tab, so always follow this navigation pan. So you will make your life much easier if you follow this pan. Go to the method specification, and under this method specification, where do you define the methods, look for this filter. You already have some categories from which you can choose. For example, if we are only dealing with one component, that component is water, then you can pretty much understand the most appropriate system or the method should be from the water, and see what are the recommended methods for that water. We have only a list of 4 methods anymore. So if you are dealing with, let's say, another system, let's say you have the system from alkali industry that makes electrolytes in the system. So what methods do we have? Here is a list of only couple of options. Rather than from the list of 50 or 60 methods, we end up with a list of 5 or 6 methods. So that is one way. Use the default filter from here, but for that case you need to have a good sense of the system itself, what kind of processes that you are dealing with. Other approach is you can use this tool, this method assistant tool, that is specifically designed to help you to choose the appropriate property method. Let's say enter the property method assistant. Again, that leads to the help. Here you need to understand, do you have a good information of the components or the good information of the process? You can check both. For example, in the process options, these are the most common process options. You can check, for example, in the first phase for the biomass conversion, and that could be an option if you are dealing with the process of, let's say, fermentation of biomass, to prepare the alcohol, or any other similar system, gasification of the biomass, or these kind of systems. Then it has already selected some of the options that are applicable, but the same filtration is already available in the upstream in the main interface, this method filter. These method filter are primarily similar to the one that looks like the processes in the help. So that could be one way if you know better about the process. Otherwise, just go back from where did we start. Otherwise you can go back from this back arrow. The other option is you have a good information of the components, then you can try what kind of components further I can screen out, general chemicals, or specifically from the hydrocarbon systems, or there are some specialty components that are termed in terms of Aspen Plus, and these are, let's say, amine systems, or the system that contain H2S particularly, or hydrogen fluoride. These have entirely a different fine-tuned methods for those systems. Or we are dealing with the refrigerants. So just based on the nature of the components and deciding whether we are talking about the pressure less than 10 bar or higher than 10 bar, you can already end up with a good window of 3, 4, or 5 methods. So at least this tool makes the life much easier to select from 3 or 4 options rather than selecting from the list of 50 methods. Okay. But before making this decision, I think this is also good to understand what exactly these methods are, or you can have a look for which method, which model is used to calculate, let's say, vapor pressure. So if you are interested in this, we can spend a couple of minutes. I have just taken a screenshot, figure 1.1, but let's enter again the Aspen Plus interface. Make any selection. Let's say we select NRTL. That is the name of the method. At the same time, NRTL is also a name of the model, and that model is activity coefficient model to estimate the activity coefficient in the liquid phase. So it's the name of the model fundamentally, but they have also named the method by NRTL. So select this model, select this method. Some quick information is just given below this method selection. You can see vapor equation of state, ESIG, this tag. We'll explore it further. Liquid gamma, GMR, ENON, all these abbreviations are also defined in the help as well. If you just wonder, you can search any abbreviation. Similarly, liquid molar enthalpy, something is written, some code is written, and these are in fact the models, math equations that they are referring to. But how to see the details? If you just go one window below, in the navigation pane where the selected method is mentioned, just open it, selected method, and here you see three tabs: routes, models, and comments. Let's have a look on the models. On the model second tab, these are the different properties, and for every property some specific model is chosen over here. Let's say the first one is 5e max. If you just take the cursor onto it, it will give a quick snapshot of the term. It's a fugacity coefficient of component in the mixture. Fugacity coefficient of any individual component in the mixture. And against it, it's mentioned as ESIG, and that is ideal gas equation of state model. Yeah. So for NRTL, the fugacity coefficient is estimated by the ideal gas equation of state from the PV equals RT. That is the ideal gas equations. So that ideal gas equation is the fundamental to the estimation of fugacity coefficient, and that fugacity coefficient is incorporated in the NRTL method. If you want to change this equation, but that should be very careful decision, you can select any other option, and all these options you can choose from the drop down. These are all equations related to the estimation of fugacity coefficient of a component in the mixture. For example, this one is Sauve-Redlich-Fonck equation of state, that is temperature dependent. You can change the method by choosing any appropriate model from here. And similarly, the second one is gamma. Gamma is the activity coefficient, and that is the coefficient or the number that indicates how liquid behaves with reference to its ideal liquid behavior. You can see multiple options over here, and right now it's taken as Renon, that is the another name of NRTL for liquid phase activity coefficient. You can just scroll this option and see other activity coefficient models as well. So these are the models, and models are exactly the math equations, and all these math equations clumped together make one method that is termed as NRTL. So selecting NRTL means we are selecting a bunch of other equations, and which are those equations for which parameter you can see from this list. For example, we can look for another one. Let's say the Ks, that is the thermal conductivity of any solid component, and you see some other specific polynomial type model is used for that. But more interesting is it also guides if you change this method, what kind of other properties are affected by this variation, and that you can simply select this affected properties. If you just click this, it will guide to the dependent properties. For example, if you make any variation in the activity coefficient model, it's not only the calculation of activity coefficient that is affected, it changes the liquid mixture enthalpy calculation, its Gibbs energy calculation, its entropy calculation as well, because all these three properties, thermodynamic properties, that directly depend on the activity coefficient when the method is selected as the activity coefficient. So that's why it should have been very careful decision to select any method before proceeding to any other process simulation. Any question from this section, or you want to explore anything further? Okay, So let's dig down further, make a use of a very simple system. Let's say we are taking a system of one component is water and other component is ethanol. Yeah? That is well known non-ideal system, water and alcohol. After selection of the component, you can click next. It will lead to whatever the next input window is. And just notice from the navigation pane, where are we now? We are under the methods folder, in the parameters folder, and from the parameters folder we are inside NRTL1. So here there is one thing, source. You can have a look from the drop down. There are multiple sources, and then there are a couple of numbers, and these numbers are AIJ, AJI, BIJ. You can just scroll to the right, and at the end you can see lower temperature and upper temperature limits for the applicability of these numbers. What exactly these numbers are? Can you just make a guess? What are these numbers? Okay, so these are the numbers that are used to determine the activity coefficient. So how do we determine the activity coefficient when the model is selected as NRTL? You can simply click this help option, this lower help option, not the main one, just right above this source. Just go to this help option and you land on this a sort of weird equation. That is the NRTL equation. On the left you have this activity coefficient gamma, and on the right side you have bunch of other parameters multiplied with the liquid composition X. And those parameters in the main equation like G, tau, these are subdefined. For example, G is a function of tau and alpha. And even tau is further defined as Aij, Bij, Cij and F. So you can notice the guide even below this. In the second table, where NRTL 1, 2, 3, 4, 5, these numbers are given in the first column. In the second column there is a corresponding symbol, and that symbol is exactly taken from the same equation. For example, this Aij, this is from the tau ij, and tau is some parameter that is used in the main equation. So this first entry NRTL1 is the entry number 1, and which that entry is in the table, this first entry Aij. That Aij, this number 3.45 is exactly over there in the activity coefficient model. So if you change any of these numbers, that means you are directly playing with this equation, with these parameters, and exactly playing with the calculation of activity coefficient. So by default, when we select the data banks from the components, so wherever those activity coefficient parameters are available, it makes a list over here and displays the number. VLE-HOC, there is another database, that experimental database that is used to calculate these numbers. If you change a different number, different source, you can see there is a change in these numbers. There can be a difference between the numbers, or there can be a difference between having different methods to solve the same system. And the decision is not only on the method name, decision is also on the rightly using these numbers. So if the system is not rightly working, you have the right method that is proposed or recommended by someone, still it's not getting the same results, there could be a possibility these numbers are not good to go for that system. And if that situation arises, then there is another option to regress these numbers from the experimental data. We can directly use the experimental data from somewhere and perform the regression and analysis and get these numbers once back and manually use these numbers. So any number in Aspen Plus that is in blue color, we can replace that number. So for example, this is 0.0, we can give a 0.01 over here, and that entire equation is replaced by another set of numbers. Surely it will take some time to absorb all this information, but that is a very critical information to enter before entering the simulation environment. Okay, anything to add? Next we have active participation from your side. Will fetch some data and perform some analysis. If you want to have 5-minute refreshment, then this is a good time. Otherwise we have to go in a sequence for like 45 minutes. 10 minutes? Okay, so we'll be back at 6:05. So 3 activities हैं what we are going to do. What is NIST data bank, उस data bank को explore करेंगे and we will try to retrieve some experimental data. Then there are 2 other exercises. One exercise is will perform property analysis of a pure component, then property analysis of a binary mixture. Yeah. So stay with me. आप साथ साथ exercise करते रहिए. जहाँ पे भी किसी को भी कोई stuck feel होता है, let me know, because we need to be on the same page during this exercise. Okay, let's be on this page. Aspen Plus 2 components defined, water and ethanol, and as of now let's remove this method. जो method selection की हुई है, वो मेथड नेम से डिलीट करेंगे ना कीबोर्ड से, तो वो डिलीट हो जाएगा. राइट, सो दैट मीन्स राइट नाउ वी आर नॉट अबाउट द मेथड, वी आर अबाउट द कंपोनेंट एंड द डेटाबेस. कौन सा? वो पहले क्योंकि मेथड की सिलेक्शन यहाँ पे की हुई थी NRTL. सो इफ इट्स सिलेक्टेड एंड यू डोंट वांट दिस, जस्ट select it and delete from the keyboard. No, it will go away. Okay, so Aspen Plus has by default a rich library of experimental data points for the pure component, for the binary mixtures, and some of the ternary mixtures as well. And that data is stored under NIST Data Bank. This a small icon at the top and the data source, NIST. That's National Institute of Standard Technology, something like this. So they provide open source data source, and that data source is used for so many other process simulators as well. There are the other 2, Dakima and Dipper. I think we need to pay for them. But anyway, whatever we need, that's available in the NIST data bank. Just enter the NIST data bank, click it, and then we are offered with the 3 options, whether we are talking about the pure component property data points or the binary or the ternary. Let's enter the pure component. For the pure component, we can only select one of the available. That's a water. Okay, because we can recognize couple of informations for the water. Once you select this component, then you can evaluate. A small button on the same window. So yeah, we have almost whatever the information was in the NIST data bank related to pure water, we have in front of us. And the information is of the 2 kinds. One can be scalar properties, yeah, just single number, and the other ones can be temperature dependent properties. So for all, this window gives every information, and here you can notice a few plus buttons, and that plus buttons, if you click it, it expands further. तो जहाँ पे भी ये प्लस का साइन है, that means that is not the scalar value. It has temperature dependent coefficients. लेकिन जहाँ पे प्लस नहीं है, everything else is a scalar number. For example, the critical pressure of pure water is 220 bar. We all know this. And similarly, the critical temperature of water is 647, I think that is around 373 something degrees Celsius. So these are the experimental numbers. Molecular weight is given, yeah. Freezing point is given. What else you want to see? मैं बताता हूँ, ये प्लस साइन जो है ना, ये फ्रंट विंडो में एक ही विंडो में सारी अवेलेबल प्रॉपर्टीज यहाँ पे लिस्ट कर दी हैं, लेकिन जहाँ पे प्लस साइन लगा हुआ है दैट मीन्स दैट इज नॉट अ स्केलर नंबर. इट स्टोर्स सम कोएफिशिएंट्स फ्रॉम द मैथ इक्वेशंस, वो इक्वेशन जो कि उस प्रॉपर्टी को एस्टिमेट करने के लिए. Maybe you can go to heat capacity ideal gas. If water is treated as ideal gas, then if heat capacity water is treated as liquid versus gas, mean gas is taken as a reference for the estimation of the liquid heat capacity. And similarly above you can see for the solid phase as well. Heat capacity crystal 1 versus gas. So gas is taken as a reference environment, and heat capacity of the solid water in the crystal form, that is estimated. So for the liquid phase, we have multiple tabs on this page. Parameters in front of us, these are the parameters of the polynomial equations. That polynomial is used to estimate the heat capacity of water, and that is temperature dependent polynomial. Then next we have the experimental data. So you can see citation of this specific experimental data as well. For example, the number 1 data point where the heat capacity at 283.15 temperature is given, and if you click on the citation, you notice a grade citation just at the bottom. So that is exactly the source literature article from where that number is taken, and it has other heat capacity values at different temperatures. This NIST TDE is entirely a different interface. So that is developed and delivered by the NIST. So Aspen Plus took advantage of the same algorithm and embedded with this interface. So this calculation is run in that thermodata engine to predict some values, some coefficient values, and those coefficient values are taken given in the first window parameters. So these are the coefficients. These are coefficients are estimated from the same experimental data that we are looking at using a polynomial equation. So that means you can entirely rely on these numbers. You can blindly rely on these numbers. It runs some other stats as well to mention which of the data was something like outlier. It rejected that data point. Some are within the same domain, are aligned with the with the polynomial. They took the same. I hope you understand this thing. So for the statistical or for regression purposes, you need to avoid the outliers just to make a good estimation of the property or the coefficients. So that's why you can notice a separate tab on the predicted values, accept or reject. Some values have been rejected, and possibly these values were outlier. So they rejected these values, and whatever that was acceptable, it took those values, run the algorithm for the coefficient estimation, and reported those values. These are the values, experimental values, as a function of temperature. If you want to plot these, there is a plot option at the top. You only have to click this option and it will plot all the values. So some values are given in the I guess pink color, some are blue and the line is passed from them, and you can notice line is entirely passing from the blue numbers, and the blue numbers are experimental data that is accepted. and some other evaluated results with the line. Experimental data, some rejected with this green, and some predicted values with the, yeah. As of now, we are not using any method to do this job. I was expecting the predicted values should be aligned with the straight line, but somehow it's not. I'm not sure what does it mean. So as predicted values, to my understanding, should have been aligned with the line because those are the accepted numbers. So you can just get out of it. And similarly, if you are interested, you can notice any other thing. For example, vapor pressure. So for the same vapor pressure, these numbers are given. You can guess these numbers should have been used in some of the vapor pressure model equation that is a function of temperature, like the Einstein equation. Then experimental data, that is entirely as the temperature pressure curve in given most of the textbooks, and similarly the predicted and evaluated numbers. So we have experimental data for the pure component in the window front of us. Some of the values are just scalar numbers. For example, the molecular weight is the only number for water. Normal boiling point is the only number. But some properties, they depend on the temperature. So whatever it has delivered, it took the experimental numbers at different temperatures, run the regression, then reported the coefficients of the polynomials. You can take the coefficients along with the polynomials and you can work outside the Aspen Plus window as well. This is for the one component. If you want to save any of the experimental data set from here, there is an option at the bottom, save parameters. So just save parameter, a window pops up with all options and one option selected. If you want to save everything related to water, you can just check from the top checkbox, or you can select whatever is required for your case. So if you want to save this experimental data for further analysis, one possibility is we want to, because right now we don't have any thermodynamic method, we have entirely experimental data. So you want to compare how the heat capacity of the water is calculated from the experimental data, and if we assume any other thermodynamic model applicable for the same system, whether these two numbers are the values they align together or not. So for that business, we need to save this data, otherwise it will not be stored in the Aspen Plus library. So to do this job, just save parameters at the bottom of this page. So if you save it, you can save only one of the parameters or multiple. Let's see what is the exercise for the pure component analysis. Retrieve experimental data of water vapor pressure as function of temperature. So preferably we need to store the vapor pressure data from the experiments, because we have the next exercise on the vapor pressure of the liquid phase. The above one should be for the ice sublimation, that is crystal with reference to gas. That should be for the solid phase, and that could have been a data of vapor pressure, that is for the sublimation. So just save the vapor pressure liquid versus gas. Yes, we want to save this data, and data is saved. Just notice where is saved. Parameters. Under the parameter. So the source is user in front of us. So that because we have not selected any of the method, if we had selected any of the method, then it could run the method on the experimental data and then retrieve the parameters as per the method. Now we are entirely relying on the experimental data, not working inside the method but working with the thermodata engine, that is another interface. So now we are picking some numbers from the thermodata engine and that directly giving to the Aspen Plus to whatever further analysis. And that is a Wagner equation. And Wagner equation for vapor pressure. You can also go from this data option. There is an option at the bottom. Yeah, data. You can use this option to fetch any property from the experimental data source. For that purpose, now the data is not stored. What is stored? Data mean actual experimental values are not stored. What is stored? The coefficients for the Wagner equation. Only that information is stored. If we want to store the experimental information, let's see if that gives an option. Above tab, the same tab that will appear in the tab over here. Let's see if we go to the experimental data and try to save this data from the bottom. So previously it was save parameters, and now it is save data, and data is temperature versus vapor pressure. So now vapor pressure, liquid versus save accepted data only. Okay, that's a good option. That means we are not saving the rejected data points. Now notice where it's stored. It's stored under the data. Yeah? So that means that is a raw data that we can use as an experimental information for any type of validation or analysis. Just go to this again thermodata engine, the previous window where every information was stored. Rather than from the parameters tab, go to this experimental data tab. Yeah? And there is a save data at the bottom option. Everyone on the same page? So we have stored experimental data as a raw form and also retrieved the Wagner coefficient values that are entirely based on the experimental information. So these two are required for us. This is one of the way to retrieve the information. Other way is, if you just notice in the component specification tab, where we have defined the components, and there is an option of review just below the component list, and that is not active as of now. There is another option. If you go to the above group, tools group, above the same window, where the retrieve parameter option is there, and it's also great so far, and both are to retrieve the parametric information, but right now they are not active. So that means that has to be another way to retrieve the information. Let's say we define a method. Go to the method specification. Let's say what should we choose as a method? We are talking about the ethanol. Let's fairly take an NRTL for this system, water ethanol. Anyway, Pang Robinson is not a good choice for this. So we have defined the NRTL and look back around the retrieve parameter from the tools. Yeah, now it's active. And also the review option is active. So that means whatever we retrieve now, it has something to do with the method. Let's say first click on the review. So it's retrieved some of the information, and look at the information. First look at where it's located now from the navigation pane. It's in the pure component tab under parameters, and right now we are on the one of the window that is named as review 1. And what kind of information is? Again some gravity. Yeah, now the heat of formations are given. Gibbs energy formation, enthalpy formation, entropy formation. These numbers are also given. What else? Molecular weight is given, critical numbers. So now these numbers are not exactly the numbers that are from the NIST data bank. Now these numbers are the other numbers. They can be entirely the same or they can be slightly different. But now the numbers are based on the NRTL method, and NRTL method intrinsically have the structural information of all the components, and based on the structure, molecular structure, it calculates some of the properties, and some of the properties are estimated by the method based on some data bank information जिस पे NRTL बेस कर रहा होगा. And that data bank is now, if you go back to the component specification in the enterprise database, ये component folder में just below the selected components you see the option of review. You haven't defined the method, then just select NRTL in the method. Okay, so now those numbers are based on this enterprise database, but now information is not entirely based on NIST TRC, but rather from the pure. The first data bank that is base for the estimation of the properties is pure 40. If the component is not located in the pure 40, then it will search aqueous. Still, if it's not found, then it's solids. Similarly, it goes down to the list. It's quite possible the numbers you see in the review option are different from the numbers you retrieve from the NIST TRC, because we are talking about different data banks or databases so far. For the pure components, that is hardly the case. I think all the information is well established, and even you can find in the most of the handbooks, even you can find information in the encyclopedias जो कि chemical engineering से relevant है या component chemistry से relevant है. You can find this information there, but you can expect a difference. Even the interesting thing is, if you go back to the review option, the same under pure component, you can change any of this number. Even you can make a very hard mistake कि ये इसका जो molecular weight है water का, rather than 18.01 you can make it 0. It doesn't mind. It's an editable number, you can change it. If it's a 0, that doesn't mean it's taken from some reference, you have changed it. And this is particularly relevant. Sometimes we have to change the information, and that cases are when you are dealing with some of the component and that component is not available in any of the data bank that is in Aspen Plus. That means you don't have any of the information about that component. You can talk about so many pharmaceutical components and biocomposite components. Those information is not still available, क्योंकि पहले वो लिटरेचर पब्लिश होता है, फिर उसके बाद उसका डाटा बैंक कंपाइल होता है, NIST के पास जाता है, फिर एस्पेन प्लस वर्जन अपडेट करके वो इन्फॉर्मेशन को फैच करता है और स्टोर करता है. दैट इज़ क्वाइट पॉसिबल दैन component you are talking, it's not available. So this is how it works. And for that kind of components, you can define as a user defined component. You can create your own component, and you can even enlist all these properties as a user defined component. That component can work perfectly fine. Similarly, you can notice other CPIG. No? These are all vector properties, some temperature dependent properties, and only the scalar properties are mentioned in the review option. You can retrieve the same information not from the review in the component specification option over here. You can retrieve directly from this option, retrieve option. You will get the same information. That is entirely different option to do the same job. If you don't like the parameters, you can clean them. Yeah? There is option above to clean those. You don't like the retrieved information, rather than deleting one by one, you can simply clean everything and again retrieve from the fresh data banks. Change the data bank, retrieve the information. If you don't like it, clean it, change the data bank, retrieve again. So sometimes we have to do this. It's not only for fun, sometimes we have to do this. Okay. Let's say we are talking about this data, that is experimental data of the vapor pressure of water. In the first setup window we have some options, but exactly the data is in the second tab named as data. These are experimental numbers. Mind the units, temperature is in Kelvin and pressure is in Newton per square meter. We cannot change it. That was experimental numbers, exactly the numbers, and we have selected as it is. Even if we change the unit, we end up with some mistake. We perform the property estimation, but the data that we are using was originally available in Kelvin. We have changed it to other unit, and that doesn't change the numbers. So let's plot this. You have option of data curve or properties, both will do the same job. You can just click one of the option, let's say properties versus temperature. So that is on the x-axis it's temperature, and on the y-axis it's vapor pressure. You can slightly play with this graph as well, because whenever you plot a graph, two additional windows pop up at the top. One menu is the design menu, the other menu is the format menu. From the format menu you can play with this. Even in there is an option to make it a square plot. If you don't like the large rectangular, you can make it square. If you don't like these numbers displayed like this, you can select the axis and change font, size, range. You can do all these options, but let's forget it because that's not the job as of now. Make it bigger one, uncheck the square. Okay, let's get back. Mind, this is experimental data. Let's now simulate the water system using NRTL method, and that is analysis feature, and you can get the analysis feature from the home tab. Go on the right, that is a pure component from the analysis group. That means if we have the experimental data, we can get similar data from the analysis using NRTL method. Okay, let's enter this pure. We landed in the analysis section below the data on the navigation pane. Everyone there? Okay. You can notice multiple options in this window. The relevant option is the first one. For this analysis, what method we have to use? You can change previously or you can change right from this page. Let's stick to the NRTL. What kind of analysis we can perform? Thermodynamic, transport, or let's say display all available options. Display all available options. We want to have analysis of vapor pressure. Vapor pressure is named as PL. Just locate the PL. Yeah, it's somewhere near the bottom. Liquid vapor pressure, PL. Or you can simply click from the keyboard P and all the options of the P will appear. Units, that is important because whatever the data we are trying to compare with is given in terms of newtons per square meter. So if we want to compare head to head, then we have to have the same unit, Newton per square meter. Liquid phase, right? Temperature unit should be Kelvin because the reference data is in Kelvin. The range of temperature we can check from the graph. What was the range? The range was 270 on right side for my window and 666 on the left. So the Kelvin temperature range is from 270 till, let's say, 665. We can do analysis in this range. Go back to the same analysis window. You can just go to the next tab. It was on the tab. Or you can go from the menu bar at the input option. So in the Kelvin we have 270, 278, let's say. It doesn't make a big difference. We need a fair window from 665 Kelvin. Just ignore the pressure, whatever is given. But shift the water from the available components to the selected components. Yeah. Now see the status at the bottom. Required properties input complete. That means we are good to run. Until unless this status is not red, we cannot run the simulation. It has to be other than the red. So now you can run the analysis either from the top or directly when in as a small button is given, run analysis. So you can click this run analysis option. You can click the top analysis also. So this is pure component vapor pressure as a function of temperature. We can merge the two plots. Previously we had the experimental one. Now we have the theoretically estimated based on the NRTL method. You can merge them. Before merging, notice one thing, units should have been same. If there are different units, that means we are trying to compare entirely different things. The units are Newton per square meter and Kelvin on both charts, so we are good to go. Then there is an option in the design menu. Option is merge plots. So we can merge the current window with other available window, and the other available window was this D1, that was database graph. If you just click on this other option, it will merge the two windows. So that means there were two graphs, now we have one graph. One is it looks like non-linear, that looks like a linear one. But beyond that, check the scale. Because on my window, the higher value was on the left side and the lower value was on the right side. So if that's the case, you have to have the same values. Okay. So actually what happened, see the y-axis scale. Just notice the y-axis scale. We have entirely different ranges on the y-axis. So that is the primary reason we are looking at different lines. To make the same one y-axis, right click on the plot anywhere, and there is an option of y-axis map, and then make a single y-axis. So it will merge the two and align the lines accordingly, and click OK. Okay, so we have fairly the same lines. There are some crossing lines, probably because it's a line chart. So the two numbers in the sequence was quite apart from each other. So I directly plotted the lines between those. Otherwise, the major line is all the dotted points in the green and in the blue. So mainly the blue points still lie on the same line as the green is, only their presence in the sequence is different, and the line chart has plotted cross lines as well. That was a very simple case for the pure component, but more important is if we run the same case for the binary system, that will be more interesting. But at least you got to know how to run the analysis, how to plot the data and merge the graph. So that was the key lesson from this activity. Let's do it now, the binary system analysis, and that is the second exercise. That is a bit more interesting. Perform TXY analysis of water ethanol system using Pang-Robinson and using NRTL. So that means we are talking about two different methods, the same system. Can somebody understand what could be the result? How to do that? Let's go to the NIST data bank again. Now we will fetch a binary system. First component is water, second is ethanol. Retrieve the data. Now we have to choose two components. Okay, so if you don't see the option over here, and then there will be a TDE results window active. TDE results, there should be another tab, so automatically results are proceeded to that window. TDE results, that is another tab on the window. And this is the experimental data, literally the experimental data of water ethanol system. A lot of data points for vapor liquid equilibrium, density, departure function values, conductivity. Everybody got to this window? Because we need to get this data. So we need to have TXY data. Yeah, that means that should be isobaric VLE data. Yeah. So isobaric VLE data is, but there are so many options how to choose between them. So if you click on the binary VLE, you can notice a lot of other windows on the right side, and every one row is a complete data set. For example, the first one is one data set that has 12 points, 12 different temperature and corresponding X and Y values, and that was published in 1899. So it's that old data. So if you click on the data itself under the isobaric, any on the data, you can see the exactly numbers. Temperature versus vapor mole fraction versus liquid mole fraction, and the original source is also given at the bottom. So that was the source from where this data is retrieved. So Aspen has also provided one tool, that is consistency test. So to pick this sort of data, you always have to perform the consistency test just to make sure the data you are choosing is of the right quality. So then go to the consistency test, and at the bottom there is an option of run consistency test. You just have to click it, and rest of the job lies with Aspen Plus. So run consistency test, it will take some time and perform different consistency criteria analysis and reveal the results. So some of data points have passed the consistency test, and even some of the criteria of the consistency test, and some have not been passed. And there is the overall quality of the data, and that you can notice from window tab 1, 2, 3, 4, 5, 6, 7. Seventh column in this overall quality data. Yeah? And you can align this quality data from 1 to 0 or 0 to 1. This is always a number between 0 to 1. 1 indicates a good quality data and 0 indicates a very poor quality data. So just align this sort, it should be descending. It should be descending. So the highest quality data should be at the top and the lowest quality data should be at the bottom. No, it should be descending, sorry. It should be descending. I always confuse the two. So highest quality data points are at the top with the 1. And the other variable is for all this one, you have different number of points in that data. So the target should be the highest quality data and the data that has the highest number of data points. So with this criteria, what I can see, VLE 068 has 36 points and it meets the quality criteria. And let's see if this is isobaric data. 068. Not over here. 068. What is this window? This is isothermal data. It's not isobaric, it's isothermal data. VLE 068. 068, no, that cannot be. That cannot be. Okay, thank you. I was looking at 062. 062 is on the isothermal. Thank you. So 068 is the isobaric data. So to save this, go to the experimental data, previous tab, experimental. We can save the experimental data from the experimental tab. 068, yeah, this one, and at the bottom we have the save data option. So save data. Just cross check, that should have been checked by default. 068, yeah, the blue one. Just save it. And now the data is gone in the folder data in the navigation pane, and the name is by default given as BVLE 068. And if you are on the data tab, the उसको सेव कर देना, उसके ना नीचे बॉटम पे होगा सेव ऑप्शन, एक्सपेरिमेंटल वाली टैब में, नॉट ऑन द कंसिस्टेंसी, एक्सपेरिमेंटल वाली टैब में. Everybody saved the data? So if you want to view the data, then the second tab is where temperature versus x versus y, that is given, but important is we can plot it, txy. Yeah, so that is isobaric data, and these are the experimental data points. Experimental data points. To plot, go to the data in the folder and simply UV the plot option of txy. So this is experimental txy. That means we have to get the estimated by NRTL method as well. Okay, so since NRTL is already selected, let's do this job first and then we can come back and plot with the Peng Robinson. To do the analysis, in the home tab, now we have to have the binary analysis option, not the pure component but the binary analysis. Go to the binary analysis, and luckily txy is selected by default on the binary analysis. Just notice from the left side we are under the analysis folder in the binary analysis input. txy two components are selected. What we have to do is the pressure exactly the same that is for the experimental data, and the composition range is always between 0 and 1. We only have to match the pressure. So what was the pressure? Go to the data, and the pressure was 10130. So 101 kilopascal in fact. So we can change this pressure from 1 atm to 101,000 and change the unit from bar to Newton per square meter. So change the pressure because that will have the effect. So pressure is 10130 in Newton per square meter, and that's it. We can run the analysis. Okay, run the analysis. Yeah, this is a very continuous plot. Temperature is in degrees Celsius. Note it, temperature is in degrees Celsius. If we want to change, we still have the option to change the units. From the design menu, there is an option to change the unit from degrees Celsius to Kelvin. I believe the other one was in Kelvin. Yeah, that was in Kelvin. So once the two scales are the same, their units are the same, that means we can cross check, we can validate. For the validation, again we can merge the plots. So for merging, you have to have two plots active on the window. If you close the previous one, then we don't see the merging option anymore. So now let's merge and then make a single y-axis. So to make a single y-axis already looks the same. Anyway, still merge to single y-axis. So now we have the response of NRTL to the experimental data. Uh, what we call it? It's acceptable or not? NRTL. To me, this is pretty good. It's already pretty good. Of course, you can see the difference between the experimental and the theoretical. Let's give a very quick try to Peng Robinson. That is the last activity of today. From the specification of methods, change NRTL to Peng Robinson. Peng Robinson. Yeah. Go back to the same analysis window, binary analysis window, to cross check whether that Peng Robinson is now active in this analysis as well. So just to cross check, on the analysis window, analysis, binary analysis input, but the third tab. First is binary analysis, then the tabulate, then calculation option. In the calculation option, we still have the NRT. So that means whatever we have done, it won't be effective unless this is Peng Robinson. So make it to Peng Robinson. Hit enter. That means now we are good to go for binary analysis using Peng Robinson equation of state. Go to the binary analysis window again and run the analysis. Yeah, you see? Okay, let's merge on the previous plot. Merge on the previous plot. Make the units to Kelvin. Merge with the BLE 068. Okay. And make the single y-axis. So this is how Peng Robinson equation of state looks like. And it's nowhere even close to the experimental data or NRTL. Make a single y-axis. So this is always the first exercise before choosing any unknown method, just to make sure whatever the method we are selecting, it's the right method for the given system. It's a good activity for the two components, but when we have more than two components, then binary analysis to नहीं किया जा सकेगा. So then there are other options to verify, and then we'll do it in the next slide.